Hi everyone, so I've graphed a polynomial here and not given you its formula because that's not the point, but I have labeled some areas. And I'm going to talk about sketching an accurate antiderivative, and I'm also going to talk a little bit about the notation you should be learning in 1.8 right now. So the 1.8 part actually shows up first thing right in the directions. So right here, this sketch direction, when you see a function defined in this weird way where you input the upper limit of integration, so basically you're calculating areas under little g, that function that you just created without any questioning is automatically an antiderivative of little g. So when you see directions like this, first and foremost, you need to recognize, sorry, can't say it and write it at the same time, that's saying sketch an antiderivative of little g. But then the second thing is you need to recognize just a little bit more than that, because this is not the general antiderivative, this is a specific antiderivative. And the plus c part of that specific antiderivative is basically determined by that too. But interestingly, what this tells us isn't necessarily a y-intercept. What it tells us is an x-intercept. And the reason for that is, notice whatever that bottom number is, let me switch to my pen. If you take big G of that exact same number, it becomes the integral from 2 to 2 of little g. And that is, no matter what function you're working with, always 0. So that bottom number tells you where the graph has to cross the x-axis, which means this is our starting point and we have to work out from there. A really common mistake in the 1.8 version of this question is to only move to the right from there. We can still move right and left. It's absolutely legal to integrate from 2 to -2 or 2 to -1 or 2 to 0. We can do all those things. So we still need to move left and right. It's just that this is the point whose coordinates we know, so we're going to use it as our starting point. So I'll start by heading to the right because that's easiest for people, but then we will also move back to the left. So what I know is that as I head to the right, little g has this area of 7.8 and it's below the axis, so that would count as a negative. We would subtract that off. And areas under little g tell you the change in y for big G. And this is the second fundamental theorem that I referenced earlier. What I just referenced is the first fundamental theorem. So it says that the integral from a to b of little g of x dx is, so this is the area, equal to big, do I want to call it g? We'll call it big F since I use g below, because this is in general, this doesn't have to be that specific one, but it will work for that specific one. So in fact, I'm just going to call it big G, same as below, because that's what we care about here. So for any antiderivative, the area under little g represents the change in y for big G. So if the area is 7.8, or if the integral is -7.8, the change in y is -7.8. So from x equals 2 to x equals 4, our y has to drop by 7.8. It started at 0, so that's going to put us at, let's see, I'm going to write this side, 4, -7.8. So note, this is really important. I kind of wish I hadn't used that 0 as a starting point, because you might lose this, but you'll see it in the next step. It's not that it's saying your y value is -7.8, it's saying your y changed by -7.8. So when we move over from 4 to 5, the area is 6.6, which means our y value is going to go up 6.6, which will leave us with what? 7.2, 1.2? -1.2. So this will be negative, 5, -1.2. Okay, so this is the first accurate piece. We can get accurate y values. The other part of accurate is I'm going to get a little pickier about your concavity and inflection point. So we'll work on that in a second, but let me first get the other side. So this is where people get a little confused. This is saying that as we move from 0 to 2, our y value drops by 7.8. So from x equals 0 to 2, big G goes down by 7.8. we know we need to end up at 0, so we just have to kind of work our way backwards and say, well, we must have started then at positive 7.8. So this is 0, 7.8, and then you can just check yourself going the right direction. So if my x goes from 0 to 2, my y went down by 7.8. That matches what the graph up above was saying, so this is excellent. And then we just need to do a little of that backwards thinking once more. The 6.6 says that as x goes from -1 to 0, my y went up 6.6, which means I would have had to start down lower. How much lower? 6.6 lower. So this is going to be -1, positive 1.2. And then that means if I go over from -1 to 0, my y should go up 6.6, and that's exactly what the graph up above was telling me. So down 7.8, this one was down another 7.8, and then this one was up by 6.6. So that's what we're seeing is those areas tell us changes in y. Okay, let's look at what our slopes are doing next. So this is now part of the usual approximate rough sketch of the antiderivative. So we know that up above, the y's tell us what our slopes will be down below. So wherever those y's are positive, we will have positive slopes. So let's see. I'm going to mark this down. So this was -1 to 0. These are all positive. Right at -1, the slope is 0, and right at 0, the slope is 0, and right at 2, the slope is 0, and at 4, again, this is really y value, but down below it will mean slope. So the y values are 0 at all of those points. In between -1 and 0, the y's are positive. In between 0 and 2, those y's are all negative. Again, negative between 2 and 4, and then positive. And then out at the ends, it's just a tiny piece, but I shouldn't leave it off. We had negative. So down below, I'm going to start with decreasing, flat, increasing, flat, decreasing, flat, decreasing again, flat, increasing, flat, and then decreasing. So a lot going on in this one. So I'm expecting to see like negative slopes and then come into a flat spot, and then positive slopes and a flat spot, and negative slopes and a flat spot, and then more negative slopes, flat, and then positive slope, flat, negative. And that's really all that tells me. So we've kind of been adding some curve to that ourselves just because we can anticipate that polynomials are going to have polynomial antiderivatives, so they'll still be curved. But this is another piece of the accurate business. We can also look at a little more detail on the little g graph, and we can actually talk about concavity, which wasn't completely neglected earlier, but I'm going to pick on it more now that we've had some more practice. So now we can look at the slopes of little g, and basically wherever little g is getting bigger, the slopes of big G are increasing. So this, where y's are getting bigger up above, slopes are getting bigger down below. And slopes getting bigger translates to concave up. So wherever this graph is increasing, the big G graph is concave up, up, up. Okay, and then the other points, let's see, I'm going to pick a different color here. What? We'll go pink. Where little g is decreasing, those are y's getting smaller, which means down below slopes will get smaller. So this is going to be concave down, and I didn't drop this down. This is going to be there, negative, negative, negative. Okay, so if you can see that through all my mess, the lines I dropped down, so right here, 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 where we hit the maxes and mins of little g, those will be the inflection points. So down below, let's say, okay, drop that down. Where was that? A little to the left of -0.5, so maybe right around here I expect to see an inflection point. And this one is maybe like, I don't know, 0.6. I expect to see an inflection point. And then right at 2, I expect to see an inflection point. And 3.3-ish. And then one more, where is this? Around 4.7. So those will all be inflection points. So I need to start with concave up until I get to that first inflection point. So I'm going to start following these slopes. We're going to go concave up. And then right at this is where I should switch to concave down. And that will continue until the next inflection point. And again, I don't perfectly hit those slopes, but I'm following the decreasing. And then we switch to concave up, and we have to hit this point right here. And this point's an interesting one. It's a flat spot and an inflection point. So basically we flatten out, but then we switch to concave down, decreasing. And we're going to, I'm getting a little bit too steep, we're going to follow that until the next inflection point where we switch back to concave up. And we follow that, concave up and increasing. And then switch back to concave down, and then we just stay concave down and decreasing. So that is a more accurate sketch. We have some accurate points, and we have some accurate inflection points. That doesn't mean the Y value of the inflection point's accurate, but the X value should be fairly accurate on those. So there's more to keep track of, but hopefully that helps. And this is both a 1.6 scale and a 1.8 scale, so you can get both of those checked off at once. Basically, this one just keeps coming back so you get more practice. Thanks for watching.